Thanks for the introduction and welcome to this talk. So today I'm going to talking about the private proof of stake blockchains using differentially-private stake distortion. So let's get started. First, let's start off with some basic preliminary knowledge about blockchains. So blockchain provides an open distributed ledgers that allows every party to publicly join, right? However, reaching the consensus for among all those parties in an open setup is kind of difficult problems. For example, we may consider about some traditional consensus protocols like the Byzantine protocols. They can help to achieve the consensus among the parties, but with some of the assumption that they will assume the total number of the Byzantine nodes will smaller than some predefined threshold. However, this fact is not true when we think about the public setup when considering about the blockchain setup, because everybody can participate in the ledger maintenance. And then the malicious nodes can easily create a lot of dummy or sibling nodes and easily surpass about the threshold over here. So blockchain implements a permissionless consensus, relies on so-called constraint resources, like the constraint computing power or the limited monetary value among the entire system, for instance, about the stake. So the well-known proof-of-stake blockchains relies on the fact that the honest party will own the majority or supermajority of the total stake among the entire system. Right? And also each of the participants, also called the miners, will also compete about the blocker proposing rights to extend about the blockchain. And the winner will take the rights to extend the chain or form a committee to decide what is the next block. Right, and typically, whoever become the wins about the block proposing elections will have more. Whoever have more constrained resources will have a higher chances to win about the block proposing election. All right, and another open problem about blockchain is that all those transactions here seems to be public, accessible to everyone. So that will also raise some of the privacy issue. And private blockchains are proposed to using cryptographic primitives to conceal all those transaction details and then leverage with the zero-knowledge proof to validate all those transactions. So they can also retain the blockchain functionalities. And for the proof-of-stake blockchains, because the stake itself is also a sensitive property, because the stake reflects a party's account balance. Also, the stake is also an additive outcome for a sequence of transactions. So we also need to hide about the exact stake value. So the zero-knowledge proof is also used for private proof-of-stake blockchains to prove about the winnership for the block for the leading election and without disclosure about parties' exact stake. All right. However, so the blockchains, even private blockchains, still suffering from certain leakages. And a recent work has been demonstrated that there's no private, proof in theory that no private blockchains ever exist that do not leak this type of leakage, which is the identity for the block proposer, right? And so even though revealing those leakages does not directly reveal some sensitive information like the stake, but remember that the frequency of a party winning the leader election is actually proportional to the constraint resource, which is the stake. So that will allow the attacker to have an interface and to play around with the hidden state. All right, so now we know that in theory that indeed we have some of the interfaces that allow some attackers to play around with the hidden state. But we want to ask the question, in practice, can we actually have an attack that can efficiently infer an unknown state associated with some honest party? And the answer is yes. So we have provided efficient stake inference attack, and they're based on two key ideas. So the key idea is based on the fact that the attacker can actually control their own transaction. For example, using transaction delay attacks, and the attacker can self-create a transaction like TX and broadcast it to everyone, but except a certain group of the parties can be chosen by the attacker. And to make those transactions, the arrival is delayed from those parties. And by doing this, the attacker can actually create a disparate in the parties, two groups of the inputs. So some group will see about the transaction, and some other group will not see the transaction. Okay. And so the key idea too is that we can actually explore the liveness guarantees supported by the underlying blockchain. For instance, we can see about the probabilistic ZT liveness guarantees over here. That is, if a transaction is received by Z fraction of the parties that behaves honestly, and then the probability that this transaction is not confirmed after T time steps can be captured by a function or a probability, which is Q1 minus ZT. Okay, and apparently if the transaction has been receiving by more parties, that means the probability that the transaction is not confirmed will be small. Okay, and then based on those two facts, let's see how we can actually do the attack. And first, I will show a simulation technique over here. So consider the attacker can, let's split the entire parties into two groups. We have victim in the one group and all the other parties in the second group. And now the attacker can create a disparity in the inputs of the two groups, the two groups. And for instance, the victim do not have some transaction and all the other parties have the transaction. And then we just simply wait for some time. And remember that the probability Tx is not confirmed after T time steps is equal to QFVT. And by repeating this simulation multiple times, the attacker can actually, or in theory, arbitrarily accurately empirically estimate the value, the probability for QFVT. Right, and by doing these simulations, the attacker is actually have the ability to simulate a biased coin with a heads probability that is tied to the victim stake. All right. However, even if we can do the arbitrarily accurate estimation for the probability, and to computing about the pre-image FV here is still very challenging. Okay, don't worry about that. We can have a second simulation strategy over here. Let's think about now we split the group into in a different way. So we have the first group is some corrupted users that are chosen by the adversary. And let's see the total stake sum up to FC. And then we do the similar simulation again. And now the attacker can actually simulate another stake-based biased coin, which the hash probability is tied to FC. And the different thing here is, so the pre-image FC right now here is actually known by the attacker, which is chosen by the attacker, right? And combining these two simulation techniques, now we can actually reduce a problem of comparing two stake values to the problem of comparing the hash probability for two simulated biased coins. And remember that if we have unlimited times of the simulations that the attacker can issue, then we can have arbitrarily accurate comparison. And then we can also compact this general proposed comparator into a tree-based like a search strategy. For instance, given unknown stake value FC, we traverse the entire search tree until hit leaf nodes, where the hash probability for the leaf nodes contains about the target. Okay, and for every time when we do a branching decision here, we are not directly comparing some values. We are actually comparing two probabilities or two stake-based bias point. And eventually we can have a search strategy or attack strategy that is sublinear time. And we have tested our attack, simulated some the attack according to the Ethereum 2.0 beacon chain specifications. And our strategy is to we simulate some random possible stake values, and then we use the stake inference attack to approximate that one. And eventually, after like 50 repeated runs, and we can achieve about so relatively stake inference errors can be just around 6%. All right, so that shows about efficiency of our attack. And so we also have strategies that can help to mitigate this kind of stake inference attack risk, which is rather than let all those parties to use their true stake in like to run about the leader election or block proposal election, we now let each party to use differentially distorted stake values, which is that they use their true stake plus some DP noise and they obtain some noisy stake and use that noisy stake values to participate in the lead election. And here, the winning probability for any parties that can extend their chain is now proportional to the noisy stake, which is DP secured and not the true stake. And then we have the method to protect about the privacy guarantee. All right. So, however, so consider about the dynamic stake settings, we will run this stake distortion within a fixed time interval and over time. So one problem is that, okay, so when we adding the noise to distort the stake, there will be some cases that is possible that the virtual stake after distortion could be larger than the pre-distortion stake, which means that the attacker can have the virtual stake increment. Okay, however, but we know that all those noises come from the DP random variables, and DP random variables actually have bounded virus. So we can actually have, so the entire virtual stake increment is also bounded. So right now, if we can set a safety goal, the post-distortion safety goal as some like a threshold, for instance, we want the post-distortion of the virtual stake to be still smaller than 1/3, and then we can actually derive another pre-distortion safety threshold over there, right? And from this, we can also see that there's actually a safety privacy trade-off with a smaller, for instance, with a smaller epsilon, and then we must pay for a decreased safety guarantee, which is smaller malicious tolerance threshold. Okay, and we also have we also do some case studies connected with the Ethereum 2 to validate about our distortion strategies. So here we also plot some like safety curves, which shows out given some of the safety guarantees or safety requirements, what are the best privacy parameters that we can configure. All right, so those curves are directly derived from our upper bounds. And then we also have on the other side, we also have some simulation results. That is, we are according to the parameters over on the safety curves, and then we just run the stake distortions to test whether we have some of the safety violations. And we can see that after 10K repeated runs of the stake distortions, we do not even see one single safety violations, which also validate about our safety curves. Okay, and lastly, we also return back to the stake inference attack. We found out that after we have coupled with the stake distortions, and then the relative inference errors for our attack strategies has dropped significantly. All right, so and then we have hit the end, so that we do a quick conclusion over here. So we know that the state-of-the-art private proof of stake designs provides liveness and safety guarantees, but we have also showed the attack that they are not sufficient in ensuring about the privacy guarantee. And we leverage about DP stake distortions that can balance these 3 dimensions, and we also observe a trade-off between the safety and privacy. And luckily, because we have the privacy is also followed by the differential privacy, so we also have a tunable privacy object. So if you are interested in this work, feel free to check our full paper over there, and feel free to ask me any questions over here. Thank you.